Hey guys, and welcome to our fourth installment of Not the Ideal Medium for Teaching Physics. Now we're going to talk about quantum physics. Quantum physics, or quantum mechanics, is the study of how very small things work. We're talking about electrons, atoms, molecules, just like really small things. Primarily sizes on the scale of 10 to the minus 9 meters. When we see something, we bounce light waves off of it. Remember that not all light is visible. A clear image involves light on the same scale as the object that we're looking at. Here we have some different sizes of wavelengths. We go from the visible to the UV, X-ray to gamma. Microscopes work by reflecting visible light off of a specimen. Now imagine, though, that we want to look at something smaller than a bug. I don't know. I don't really use microscopes. Imagine that we want to look at the structure of graphite. Imagine we want to look at the structure of graphite, a simple cubic lattice. This can be oversimplified as a bunch of planes of atoms stacked neatly. Think of each atom as a barrier, and the space between atoms as slits. Light will travel through the slits until it hits an atom that reflects it. The light will be reflected at its angle of incidence and emerge on the other side. The waves that emerge will overlap with an extra distance of delta r. In this case, delta r is equal to d cosine theta. We get an overlap that's constructive when delta r equals m lambda, or when the net extra path length is equal to an integer number of the wavelengths. We see here that each wave, it travels an extra d cosine theta, then it also travels another. So it travels one delta r, and then it travels another. So instead of what we had in the last chapter, this is going to be close. We now get that it's constructive when 2d cosine theta equals m lambda. This is similar to what we had in the last chapter, except now we're dealing with 2 extra wavelength additions. The areas of constructive interference are called the Bragg condition. Bragg actually won the Nobel Prize for finding the spacing between diamonds. This method was also used by Rosalind Franklin to determine that DNA was a double helix. By the early 20th century, people started to think that we were onto something with this whole atoms thing. But the question that was on all the cool kids' minds was, how does light fit into the picture? Consider the observations from the next experiment. We've noticed that light causes electrons to be ejected from a cathode. Light, we have a circuit with a battery, we have a cathode and an anode, and then there's like a tube around them that lets light in on the cathode. And we are measuring the current. Light causes electrons to be ejected from the cathode. That's simple enough so far, but now let's poke it with a stick. We see that the current that we measure is directly proportional to the light intensity. So more intense light means more current. less intense light, is less current. Straightforward enough, bright light is more current. Current, we also observe that current appears immediately. There's no delay or like charging effect or anything like that. There's just an immediate current flow when the light is applied to the cathode. If the cathode is at the negative end of the battery and the anode is at the positive, current changes very little as delta V is increased. So as we increase the voltage of the battery, very little change, the current isn't really affected. Now, as any scientist would, you take a working setup and start changing things to see what happens. So now let's switch the battery. Say that the cathode is now positive and the anode is negative. Now, as we increase delta V, the current will actually decrease. At some point, the current stops completely. At this point, we say that delta V is equal to negative V stop. V stop is called the stopping potential. This is the potential difference of the battery that stops all current from the light. This is strange, but let's take a step back and think about what's actually going on. Current is moving electrons. Moving electrons have kinetic energy. We went over this in chapters 21 and 22, but let's recap. Voltage is energy per unit charge. We represented potential energy as U equals QV. Since potential energy equals kinetic energy, we can say that the maximum kinetic energy is equal to EV stop. We assume that Q is an electron and the voltage at this point is the stopping potential. At the point of, we can say that that is the kinetic energy at the point of zero current, or that V stop is equal to K max over E. This must be the condition to stop the electron from flowing. This must be the voltage that causes all of the energy to become potential. Our fourth observation is that V stop has the same value for both weak and intense light. A brighter light gives higher currents, but both are zero at V stop. Also, we only get current or electron emission if light exceeds a specific frequency. This is called the threshold frequency. This is represented by F0. This threshold frequency is dependent on the metal in the cathode. The threshold frequency is a property that a metal holds, so it's a constant across that type of metal. This can be seen in the graphs below. We get a current spike at a threshold frequency. So anything lower than the threshold frequency does not produce any current. Then we get a spike, not like a gradual increase. Current occurs here. We also see that more intense light yields higher currents. But again, intense and weak light both stop at the stopping potential. This is where we're going to stop part 1. We will pick this back up in part 2.